Today we're going to finish up our sections 4.3 and 4.4 by looking at tree diagrams and the idea of finding the probability of at least one of whatever it is that you might be looking for. Tree diagrams are an incredibly useful tool to help you figure out what your sample set is when you have multiple steps like an if-then, or you're looking for rolling a sum of two die like we'll see on one of our labs, or flipping two coins, maybe two at a time, maybe one flip right after another. In this case, in this example, I'd like to look at the probability of having a boy versus a girl. Not only because it's very popular in the Triola textbook, that overall theme of birth, but it's something that you hear a lot about amongst your friends after a certain age, where maybe they have 2 or 3 girls and they say, oh, we're going to try for a boy, or vice versa. Something that you now know about having a boy or a girl is that they are independent events, right? So you can have 20 boys in a row. That does not inherently make it more likely for you to have a girl on the 21st birth. Having said that, is it unusual to give birth 21 times? Well, period, yes, but to have 21 births and have them all be boys, absolutely, and this is why. Let's say that we want to have 3 children. So I go and have my first child, and it could obviously be a boy or a girl. Now, because of what happens next, these guys are independent events. Whether or not I had the boy first, I could still have a boy or a girl. Or if I had the girl first, I can have a boy or a girl. And you might say that, you have a finite number of resources in there, and if there's some way that you can count them all up, could you find out which one is more likely? Yes, but when you have a very large amount of something, we consider it to be independent, even if in theory, if that you're taking one away, that would make it dependent, because it's going to have a less than a 5% impact on their overall total. So this is my first child, this is my second. Let's have a third. So if I had 2 boys, I could still have another boy. Nothing changes, or I could finally have that girl. And I finish out my tree diagram, and you can see the tree diagram is starting to get a little squished, and that happens after 3 or 4. These tree diagrams can get very big, even with very simple examples. So usually we only go 3 or 4 steps. It's easy to check to make sure that we found everything, because I have 2 things that can happen during the first birth, right? Boy or girl, 2 on the second, 2 on the third. So when all's said and done, I should have 8 what we'll find to be permutations, although most likely you would hear them say as combinations. I could have boy, boy, boy. I can have boy, boy, girl, right? So imagine putting a marble and it falls down the limbs. I could have boy, girl, boy. I can have boy, girl, girl. Over to the girl side, I can have girl, boy, boy. I can have girl, boy, girl. Girl, girl, boy. I'm kind of messing up my capital and lowercase, and then finally girl, 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 right? So I have all 8 accounted for. So if I wanted to know find the probability of having all boys, that would be pretty easy, right? There's only one that has all boys out of the 8, so the probability of having all boys, and I'm going to scroll down a little bit, is 1 in 8, and you can see it's the same for girls. So as you go on and on, the theory of having all of one gender is unusual, right? So if I did another level, the probability of having 4 boys would be 1 in 16. So it becomes more and more unlikely that you would have all the same gender. So then what's the probability, if we'll stick with 3 births, of having, and here comes the magic line, at least 1 girl? Well, there's lots of different ways that I can have at least 1. I could have 1, like in this example right here, or in this example right here. I could have 2, like in this one or this one, actually this one as well. Oh, and there is another 1. Or I could have all 3 girls. That would be at least 1. We're not counting boys for the sake of this example. And so there would be 7 different ways that I can have at least 1 girl. The exact opposite of having all boys, right? So if you have at least 1 girl, then you can't have all boys. This was a pretty small set, so I can just go ahead and make my tree diagram and look at all the possibilities and count them up. But what if it was something that was much larger? What if it was something like you had 10 births? Goodness, right? So if there was 10 births, just to kind of keep the same storyline, each time there's only 2 things that can happen, and that's going to happen 10 times. And so I can find out what 2 to the 10th power is in my calculator. So pull that up, and I will say 2 to the 10th power. There are 1,024 different permutations. Well, only one of them could be all boys. It will always work out that way, like you see here. So as we can continue down, it would always have to be boy, 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 boy. In this case, heading off to the left, although you can certainly write this in a different order. So to have all boys, there's only one way, but to have at least one girl, well, there's lots of ways. Too many to count up. So sometimes it's a lot easier to find out the one thing or handful of things that are not what you want, and then subtract it out of the one. And so any form of one will do, so we might as well pick one that has a common denominator. There's only one way that I can get all boys. And so what's the probability in 10 births? You will have at least one girl, as you would imagine, a whole lot. 1,023 over 1,024. And so that's the idea of using at least one to shorten the process of counting up all the things that fulfill what you want. But let's also look at that rule that I was talking about a little bit earlier about when you have a lot of something to count for, even though theoretically they're dependent. When there's so many, we assume that the rule for dependent or independent will apply. So in number 11 and 4.4, you have a tire company. It makes 6,500 tires. 300 are defective. So if I were to pull 4 tires out, what's the probability that they will all be good? So if they're all good, I have 6,500 to choose from. 300 are defective, so that means that 6,200 are good. Now, if you're going to take a tire out and you're going to put it on the car, when you go back in to pick out another one, you can't include the one that's already on the car, right? So now you got 6,499, and assuming that we got what we wanted the first time, there's 6,199 that are still good. And I go in and I get the 3rd tire, and I go in and I get the 4th tire. And now I can use my calculator to take care of all these very big numbers for me. We will make sure that we typed everything in the right way. We did not. I got a 5 right there. And so your probability is about 83%. 8277. 8277. And depending how they want you to write it, most likely a decimal to 4 places, that would be fine. And in case that they want a fraction, you can hit math, enter, enter. And if it were nice, usually it changes it back. This time it didn't. So I'm going to guess that they are okay. Yep, with the decimal. So 0.828. So now, for whatever reason, you have to go in and pull out 100 tires. Well, you certainly don't want to do this process 96 more times. Now, pulling out 1 tire is only representative of a very, very small percentage, right? So I would take this decimal point back 3 spots. So I'm talking about 4 spots and have to add in 3 zeros. So I'm talking about 0.01%. Much, much smaller than the 5% rule. So if the impact of removing 1 is going to be representative of less than 5% of your overall total, then we can go ahead and pretend that these guys are independent, that what happens first won't impact what happens next. So the probability of picking a good tire is 6,200 out of 6,500, and we're just going to kind of pretend that that's the same for all of them, and pull out 100. I can reduce this a little bit even in typing this in. I can say 62 over 65 and just reduce those zeros, raise this to the 100, and I have 0.009 when I round. I'll leave it as 88 for now. So as a percent, 0.88%. So if you had to go in and pull out 100 tires, even though only 300 are defective, what's the probability that all 100 of the tires that you pull out of the 6,500 will be good? Less than 1%. So you better have a plan of how you're going to deal with people coming back and returning defective tires.